Okay, let's take a look at two examples and see how can we actually calculate the mass moment of inertia or moment of inertia now that we know what it means. So here we have a slender bar, and slender, by the way, means that the bar's length is much greater than its width, so we can safely ignore the width and just take into account the effect of the length of the bar. Now this bar has a mass of m, a uniform cross-section area of A. The whole length is L, lowercase l, and we're trying to find out what is the mass moment of inertia around the axis L, uppercase L, passing through the center of mass. So I'll start with the equation I introduced. I is equal to integral r squared dm. And if I consider a small element of mass in this bar, let's say here, let's say this is dm, and dm is at some distant r from where I want to find the area moment of inertia about it. Dm, now I have to find a way to take this integral. So dm, I have to turn it into something more familiar, probably relate that to the geometry of the bar. And I can do it using the definition of density. I know density is mass over volume, and volume is nothing but area times length. So area times length for a bar. So I can write the equation for that small element as dm is equal to rho a dr. So rho is density is equal to mass divided by a times dr. So I can replace this into the equation, to the integral. I was trying to come up with a way that relates this integral to geometry so I can take this integral. So I wrote it this element of mass as a function of density, area, and how far is that from the axis of rotation, using the general definition of density. If I replace that, I becomes integral rho a, let me write it this way, r squared dr. And dr changes how? R changes from minus L over 2 to L over 2, right? This is, if this is the center, 0, it goes to L over 2 this way and minus L over 2 this way. So the limit for this integral becomes minus L over 2, L over 2, since I'm taking the integral over R. Now, rho A is constant, so I take it out. Minus L over 2, L over 2, R squared dr. And we can take that integral and plug in the values. So it would be r to 3 over 3 from minus L over 2, L over 2. Which means I becomes, if you replace that, you will get 1 over 12 rho A L to 3. Now, this is good. This is pretty much the moment of inertia for a slender bar rotating around its center. But we are usually given the mass, not the area and density. So what I'm going to do is that I'll do the reverse and convert this into mass. So rho is equal to m over v, which means it's equal to m over a, and the length of the bar is L. I replace the rho with m over a times L, and I'll get what I was looking for, which is the mass moment of inertia of a slender bar about its center of mass. This is a very important equation. We'll use this over and over. Now, that was a slender bar, pretty straightforward. Now let's take a look at another example. The second example would be a plate. In this example, I have a homogeneous flat plate, some shape, that the shape is not specified. It has a mass of m, and it's uniform, and the thickness of the plate is t. The thickness is uniform and it's t. Now, considering this Cartesian coordinate system, I'm asked to find mass moment of inertias. Now, here we have three axes, right? We have x-axis, we have y-axis, and we have z-axis here coming out of the screen. So We have three axes, which means we can find three, I'll put it here, Z. We can find three moment of inertias. So again, I'll write the equation. I is equal to integral r squared dr. Sorry, r squared dm. Right? That was the general form of the equation. Now in this case, I'll do the same thing as I did for a bar. I try to find a way to take this integral, so I want to relate this integral to the geometry of this plate. Let's take a small element, this element there. Let's say the mass of the element is dm, the area of this element is dA, and it's at some distance r. Right? Here is, let's say, x, and here is y. Now, again, I'll go for the definition of density. Rho is equal to m over v, and m over v is nothing but area times thickness, so AT. From there, I can get m is equal to rho AT. Differentiate both sides, dm would be rho A dt is the thickness is fixed, so there is no differentiation there. There is no change there, so it would be rho t dA, the area that is going to change based on what is the area of this object, right? This flat homogeneous plate. Now I plug this in to the equation for the moment of inertia. If I plug that in, I will get let me write it here. I'm going to specify that with z, because this is the mass moment of inertia about z axis, and I'll put a small m here just in this case to you'll see why, to identify this from area moment of inertia. That'll be rho t r squared dA, and now I'll take this integral over area. Well, rho t comes out, integral r squared dA over area. Now what is this? This is what we have seen before. We have to take this integral, but we don't really need to calculate that because this is something that we have seen before. This is nothing but the polar area moment of inertia. If you remember again from statics, this is polar area moment of inertia. And I'm going to show it with J naught here. I don't know what the letter you use in statics, but accept this from me as the letter to identify the polar area moment of inertia. So the r squared dA. This is the polar moment of inertia again, from statics. If you have your notes, you can take a look at it. That's related to the area. So we can see that the mass moment of inertia around z-axis is related to the polar area moment of inertia. I can write it. Let's see if I can even more simplify that. So IZM would be m. Well, not quite there. So that would be rho t j naught. Now, following what I did for the bar, as I said, we don't want to see density in the equation, we want to see mass. So I'll use this one. Let's put it this way. You know what? You actually have it there. So rho is equal to m over at. From here, you can see that rho t is m over a. So I can replace rho t with m and a. That gives you m over a j naught. That would be the mass moment of inertia of a homogeneous flat plate about z-axis. Now, following the same process for x-axis, right? X-axis, what do we have here? Well, the general equation is r squared over r squared times dm. Now, r squared is a distance of the element from the axis we are trying to find the moment of inertia about it. When we want to find it about x-axis, the distance of this element is here. It's y. So now the distance squared is y squared. That would be y squared dm. And the rest is pretty much the same story. We replace rho t y squared dA. Right? We replace rho t dA from density. And we have rho t y squared dA, the integral over area. Now this is again something you have seen before. This is nothing but the area moment of inertia about x-axis. This is area moment of inertia about x-axis. What is it? Oh, now you see why I used the notation m at the bottom of for superscript when I was defining Ix for the mass moment of inertia, because I want to use Ix for area moment of inertia, and it's y squared dA. We'll get Ix, which I'm putting m here since we have them both in this problem, but typically we don't really put an extra m. Following the same procedure, right, to get rid of rho t, you can just put m over a instead of rho t and rewrite the equation. So that would be m over a Ix. That would be the mass moment of inertia about x-axis for a homogeneous plane. Same story for y-axis, right? The integral. Now the distance is the distance from the element to y-axis, which is x. So now we have x squared dm. That will be rho t x squared. Oops, something went wrong there. X squared dA, and that'll give you rho t integral over a x squared dE. I'm not going to write it here again, but now this is the definition of the area moment of inertia about y-axis. This is what you had before in statics. So just replace that, and you'll get the mass area moment of inertia is equal to m over a times area moment of inertia, sorry, mass moment of inertia about y-axis is equal to m over a around y. Area moment of inertia about y-axis. That would be the last one. So we got three moment of inertias, mass moment of inertias. One about z-axis, one about x-axis, another one about y-axis. And they see how they are related to area moment of inertias that we know from before. Now, one thing I want to mention is that, as I said, we use the same notation, I, right? Ix, Iy, Iz, when we're dealing with mass moment of inertia. So both of them have the same type of letter to identify them, or they use the same type of letter. One thing you can keep in mind is that the type of moment of inertia that we are using in a problem, in order to identify what type we're talking about, look at the units. Right? Mass moment of inertia, the unit for that is kilogram meter squared, while area moment of inertia is m4. So if I just want to quickly mention this. So note, to find what type of moment of inertia we're using, to find what type of moment of inertia we are using in a problem. Pay attention to the units. Attention to the units. Right? So mass, moment of inertia, I try to say mass moment of inertia and area moment of inertia, but you will see moment of inertia for both. The unit for that is kilogram meter squared, while the area moment of inertia has the unit of m²4. And also I can realize that based on the context and what the problem is talking about, aside from paying attention to units.